Hello all of you. Welcome to the 48th lecture on the course on analysis and modeling in chemical engineering. In this week, we have been discussing about separation processes. We discussed examples of separation processes, and then in the last class, we started talking about cascades, and we have also done previously the thermodynamics of the separation processes. So I will begin with some examples in this lecture, and then we will do other kinds of cascades in the following class. So, the first example, we are asked to describe in words the following k value expressions and then identify which of the following k value expressions are rigorous. And then for the non rigorous expressions, we have to cite what assumptions are being made, right? So, the first one is this, which is actually rigorous. We can quickly derive that expression. We can start from mu I L is equal to mu I V for the vapor liquid equilibrium, that because the fugacity, the partial fugacity is given as something like this, we can write the equality of chemical potential as the equality of the partial fugacities, and in terms of the partial fugacity coefficients, the partial fugacity of liquid is represented as phi IL bar into YIP, and for the vapor, phi IL into XIP, and for the vapor we have phi IV YIP, and that gives me Ki is equal to Yi by Xi is equal to phi IL bar by phi IV bar, right. So, it is clearly correct. The second one, although it appears to be correct, is not correct, because these are referring to the pure component fugacity coefficient, right. So, phi IL without the over bar is defined as something like Fi by P as opposed to phi IL, which is defined as Fi bar by Yi Xi P, right. So, clearly the pure component fugacity coefficient need not be equal to, in fact, should not be equal to the partial fugacity coefficient in the mixture. So, therefore, this is based on the assumption that the fugacity coefficient is unchanged in the mixture. It is same as whatever we had for the pure component. In the third case, we have dropped the vapor part. So, that also means that we are assuming that my phi IV is equal to 1. So, this assumes that we have an ideal gas, because phi IB is assumed to be 1, and we are also taking that phi IL is same as the pure component fugacities, that both are assumptions here. So, A is rigorous, B and C are approximate. D, as we have derived in the last lecture, is also rigorous. E is what we have got, approximating it as an ideal solution. We have got this Ki is equal to Pis by P. This Ki we have got here. This is also rigorous, because this looks very similar to what we had here. And in fact, the last one is an approximation, because we are using some kind of a modified Raoult's law, right. So, A, D and F, these are rigorous, and other required assumptions. For G, the assumption is modified Raoult's law. For E, the assumption is Raoult's law. And for C, we have assumed an ideal gas, and we also assume that the pure component fugacity coefficient of liquid is same as that for the mixture. And In B also we have an assumption that both the liquid and vapor partial fugacity coefficient is same as that of a pure component. Okay. Let us do one more example. So, here we are asked to show that the alternate separation sequences that we can have for 5 final products with 4 columns is 14, right. So, we have done it for 3 columns in the earlier class. So, we want to do it for 4 columns with 5 products, and we are assuming that each column has 1 feed and 2 output streams, right. We can of course do it by drawing all the flow sheet as we have done earlier, but I want to illustrate the same idea in terms of the trees that we have discussed in graph theory, right. So, something like this where I am extracting 2 products out of the second and third column, and the first column is basically getting the feed. I can also express this in terms of a graph, right. That is something like this. So, the first one breaks into 2 and the second node breaks into 2 and this breaks into 2, right. So, the nodes which are dangling, they are my product streams. Here we have P1, P2, P3, P4. So, the dangling ends or the free ends are my product streams, and all the other nodes becomes my column. So, this is my first column, this is my second column, this is my third column, right. So, I can have a shortcut representation of the flow sheets using these trees that would really make things easier once we have many columns involved, right. So, let us try to quickly do the trees for this particular case. So, one possibility is like this. So, you see we have 5 dangling ends that gives me P1, P2, P3, P4 and P5. And now, I mean, clearly it doesn't really matter if I switch between P2 and P3 and P4 and P5, but what still matters is this P1, whether I take it from the top or from the bottom, right. So, this will basically correspond to 2 sequences, one where P1 comes from the top and other when P1 from the bottom, right. So, this is P1 can be top and bottom. So, we have 2 sequences like this, and for other 4 it does not really matter, right. We can form one other kind of a tree. Again, we have this branch containing P1 and P2. Again, where the P1 and P2 we can interchange them, but this branch can come out from the top or from the bottom. So, we have 2 sequences from the top or bottom for P1, P2 together. I am referring to this particular branch which can be from top and bottom. Now, similarly for P3 branch, that can also be from top or bottom. So, in total we have 2 into 2, that is equal to 4 sequences. And finally, we can have something like this. Where this P1 can be top and bottom, that is two possibilities here. This P2 can be top and bottom, two possibilities here. And this P3 can also be top and bottom. The P4, P5 order doesn't matter. So in total, we have 2 into 2 into 2, that is 8 sequences. So in total, we have 2 plus 4 plus 8, that is 14 sequences, right? So the graph theory really helps us enumerate the sequences quite easily, and then we can use the remaining apparatus for the graph theory also to analyze the separation sequences in more detail. Okay, so let us take one example of a solid liquid cascade, but something that we can relate to based on our daily experience, right? So one of the simplest or traditional methods of washing clothes, if you have been to a village and have seen this old washing men, they used to wash clothes like this, but in this particular way, when we didn't have washing machines. So this involves dipping clothes in a bucket of clean water for some time, followed by draining the dirty water. So it's some kind of a batch process. You put clothes in a bucket of water. This is my cloth, and this is my water in a bucket, and then we basically drain it out. So once we drain it out, then we have dirty water coming out of this that contains some dirt, and then we basically repeat the process again by adding fresh water, right? So every time you will add water and wait for some time, provided that the cloth is sufficiently dirty, the water will get dirty and you are basically throwing away that water and again adding fresh water and again doing it, right? You may ask, what is the point of doing it, right? The point of doing this is because the dirt is going to have some finite equilibrium solubility in the water. So once it achieves that equilibrium solubility, then whatever water is there, that is no longer separating the dirt from the water. If I discard that water and add fresh water, now the dirt may again start coming in and new equilibrium is going to get established, right? So this way, by changing water after so much time is going to basically give me a new equilibrium, which will give me a more efficient removal of the dirt from the system, right? So let us assume that there are n such cleaning cycle, where each cycle means that I add water in a bucket and I put the clothes in there, and after, at the end of the cycle, I basically discard the water which I can discard, and again I add fresh water in there for the same weight of clean water in each cycle. So I'm keeping that fixed, and for a given dry weight of the clothes, and we are assuming that the ambient temperature is maintained in all cycles and there is no stirring of the bucket. We have to develop a model for the cleaning process, right? The reason we are saying no stirring is because we want to use the assumption of equilibration. So therefore, we don't want to have any kind of non-equilibrium things happening. But in general, you may also want to stir it in order to get better removal of the dirt, right? But in all we are doing now, we want to assume that we have some kind of an equilibrium attained. That is more of a numerical necessity than the actual reality, because in reality you may not have that equilibrium condition being met, right? What we also assume is my duration tau is long enough such that an equilibrium is maintained for the dirt in the water, right? So if we go back to the example of the solid liquid cascade that we have done, I can imagine that my cloth becomes now the feed. Of course, it's a batch operation, but cloth becomes the feed, which contains an insoluble component which is my cloth, and a soluble component, that is my dirt. Let me call this cloth as some C and dirt as some D, and W, water, is my solvent that is coming in. Right? So let us do it for the very first cycle. Let us say I added some, let me call this water as some mass S, just to differentiate from the W, the washing factor, which we have defined earlier, right? So in the first cycle, I begin with some D0 dirt in C cloth weight, and this is the dry weight of the cloth. This is the dry weight C. Of course, the cloth is going to take up some water, it will absorb some water, right? But this is the dry weight of cloth. And let us say we are adding some S, so I am referring to them as their masses, and S is the water that is added. So I can again define some kind of a quantity like R, which is the ratio of the mass of water absorbed in the cloth. So the cloth becomes some sort of my underflow, except that it is a batch situation. So absorbed in the cloth is definitely going to get wet, and I mean, of course, you are going to rinse the cloth, but we are assuming that we are not rinsing it. We're just removing whatever water gets away out of this. So whatever is absorbed kind of remains there at the end of the cycle, divided by the mass of dry clothes. So mass of water absorbed is therefore going to be something like R into C. Now I can define the X and Y. So X is the ratio of the mass of dirt remaining in the cloth. Let me call this some D1. So D1 is the dirt remaining after cycle 1, divided by the amount of water which is present in the underflow, which is my cloth, that is equal to RC, and my Y, that is now whatever dirt which has been taken away, right? So we had in the beginning D naught dirt. So D naught minus D1 will now go in the overflow. It will go away with the water, and basically it will be discarded after the end of the cycle. So D naught minus D1 is the dirt which has been removed in the first cycle at the end of it, divided by the amount of water in the overflow. So we started from amount of water S, out of which RC was absorbed. So S minus RC will remain here. So we have the equilibrium condition X equal to Y, and that gives me D1 by RC is equal to D naught minus D1 by S minus RC. And if I solve this, I am going to get something like D naught minus D1 by D1 is equal to S minus RC by RC, and that gives me D naught by D1 minus 1 is equal to S by RC minus 1, and therefore D naught by D1 is some kind of, again I can define a washing factor W, and therefore D1 is going to be D naught by W. That is the amount of dirt that is remaining at the end of the first cycle. Now I can go ahead and do it for the second cycle. What is given in the problem is at every cycle I am basically adding the same weight of the clean water S, but now whatever is absorbed, it is already absorbed after the first cycle, right. So now in the overflow, the amount of water will remain as S as opposed to S minus RC, because now the cloth before the beginning of the cycle is already wet, right. So for the second cycle, we are going to have something like my X is going to look like D2 by RC, and my Y is going to look like D1 minus D2 divided by S. It is not S minus RC now because I am adding same amount of fresh water. Again I do X equal to Y, and that gives me D2 by RC is D1 minus D2 by S, and that gives me D1 by D2 minus 1 is equal to S by RC, which is my factor W, which I have introduced. So my D1 by D2 becomes W plus 1, right. So my D2 therefore is D1 by W plus 1, but D1 is already D naught by W, so it is D naught by W into W plus 1. And the same thing is going to happen for all the remaining cycles. So therefore in general we can write Dn as D naught by W into W plus 1 to the power n minus 1, right. So for the first cycle we are going to have D naught by W, but for the second cycle onwards we are going to also have a factor of W plus 1, right. So you can see again I can also write the expression for a batch process also in this particular way. Now the question asks that instead of dipping clothes in the bucket, let us say I keep the clothes directly in a running water from a tap, and that is coming at some constant volumetric flow rate, and we are doing some immediate draining of the dirty water, right. So now instead of putting in a bucket, now we have an open tap. And the water is coming at some volumetric flow rate V there in the open tap, and my clothes is kind of remaining here, right. So it is something like a semi batch process because the cloth itself is not moving, but water is basically going away with the dirt, right. Now clearly equilibrium is not going to be maintained in this case because water is not remaining there for long enough time. But let us say, just for the sake of argument, if I assume that this equilibrium is instant and it happens, then we can go ahead and try to model that, right. So let's assume that we have equilibrium condition. Then in that case, you can imagine, you can look at this initial part where the water will get wet and we will have a net of the fraction of the solvent there. So let us include that in there, so that once it reaches that, now it will remain with that, right. So let's assume that the amount of water absorbed is multiplied by C. The R is constant after the water is absorbed. So the wet cloth weight is not changing. Now whatever dirt is there, and of course the dirt is present in small amounts compared to the weight of the cloth. So the dirt going out is not resulting in appreciable change in the weight of the cloth. Right? So now again, if I do this idea of equilibrium here, so my x for the cloth is going to be my dirt that is remaining in the cloth divided by my RC, and my y that is going in my overflow is my mass flow rate that is essentially going out, that will come in the denominator. It will be some function of the volumetric flow rate, but basically we have to multiply the volumetric flow rate with the density of the water. So rho into V gives me the mass flow rate of the water that is going out, and it is carrying the dirt with a certain rate, right? So let us say the dirt is going away with some rate Fd. So y becomes Fd, and what is Fd? That is basically the change in d that is happening, right? So this becomes something like minus dd by dt divided by rho v, and if I now equate x equal to y, I am going to get something like minus dd by dt is equal to d rho v by r c, and that is going to give me some sort of an exponential relation. D is equal to d naught exponential minus rho v by r c t, right? So therefore we can also derive the expression for that particular case. Now it is also asking that the use of hot water is expected to expedite the cleaning process. What the hot water is going to do? Hot water essentially will help reach the equilibrium faster. So my assumption is going to be more valid. But in principle, it can also change the absorption that is taking place, because absorption is also going to be a function of the temperature of the water, right? If I add a detergent, so in the worst possible case, you can imagine that the dirt is not going away at all. If, for example, detergent is not being put, the dirt only goes away when the detergent is there. It depends on the kind of detergent. So essentially, it is also going to have a bearing on the parameter R, and therefore it is also going to affect the washing factor. So we have to appropriately modify the washing factor or the value of R in order to account for this as well. Okay. Now, in the last class, we have done the derivation for a counter current leaching cascade, and the question asks you to repeat it for a co-current cascade where the feed and the fresh solvent enters the same stage, right? So we have done something like the counter current version of this, but now we want to do a co-current version of that where my feed and the solvent enters the same stage, right? And this also demonstrates the point why we should not do co-current, right? So let us say again we have Fa and Fb. A is my insoluble solids and B is my soluble solids coming in. So in the first stage, by the logic that we have, Fa is the amount of solvent leaving out of this, and S minus Rfa is the amount of solvent leaving from the overflow. And now in the first stage, we are going to make an equilibrium. X1 is equal to Y1. And I can of course write the material balance for this. But then once it enters the second stage, it is the same liquid that is entering the second stage. There is no change in anything that is taking place once this liquid, after reaching equilibrium, is going from stage 1 to stage 2. So therefore, in the second stage as well, we are going to have the same value of x1 and y1. It is not the same as the counter current operation. Because of the flow, the composition of the two streams were changing because they were moving in the counter current direction. But now they are both moving in the same direction. So it is like the same liquid is going from one to the other. So there is no reason a new equilibrium is going to be attained, and that's the reason why this co-current stage is not at all helpful. Provided that equilibrium is attained, it will be attained in the first stage itself, and all the subsequent stages are going to have basically the same thing. Right? Now, we are also asked that the passing problem in problem 1 can be thought of as a cascade of washing stages where fresh solvent is added in each stage. Develop a model to derive the number of stages to achieve a desired cleaning of clothes for a cross current cascade. Now we have a cross current cascade. So we can think about the same washing problem, but now we are doing in a continuous manner, but in a cross current cascade. What exactly will be a cross current cascade? So we will have stages like this. And my clothes will enter here. My clothes plus whatever dirt is present there will enter here. And I will pass fresh solvent in every stage, right? So in the very first stage, I will have, let us say, S amount of the fresh solvent. So out of this, RFA will get into the cloth. The remaining will only come out of this. But for the remaining stages, whatever S I have, the same S is going to come out because the clothes are not going to absorb any new amount of water. Right? So for all except the first stage, the amount of water that is coming in and leaving are the same, right? And let us say at the end we have some C plus Dn, right? So let's again do the balance for the stage. So for the nth stage, for n not equal to 1, we have RFA coming in of the solvent, and going out is also RFA, but the dirt dn minus 1 is coming in and dn is going out, the mass of dirt, and then S is coming here and S is going out. And if I do xn is equal to yn for the nth stage, the xn is going to be something like dn by RFA, and yn is going to be the dirt that is removed, that is dn minus 1 minus dn divided by the amount of solvent S. So essentially we have the equation similar to whatever we have obtained earlier. So we can write dn minus 1 by dn is equal to W plus 1. Now for the first stage, we have a slightly different equation. We have essentially no solvent coming in and RFA solvent going out, S coming in and S minus RFA going out. So if I do x1 is equal to y1, we are going to have and d1 going out, d naught coming in. So if we have d1 by RFA, that is equal to S d naught minus d1 by S minus RFA, right? So if we do this, we are going to get something like d naught by d1 is equal to by W. Essentially, we will get the same relation whatever we have obtained earlier for our washing problem, right? So essentially, we are going to have something like d1 is equal to d naught by W and dn is equal to d naught by W into W plus 1 to the power n minus 1, right? So with that, I conclude this lecture on these examples. In the next lecture, we will take some other separation processes like liquid-liquid extraction, vapor-liquid separations, and so on. So with that, I stop here. Thank you so much.